Hey everybody, and welcome to Predicates and Quantifiers with me. Today we're going to be discussing how to talk about truth values for ambiguous statements. For instance, consider the following fake phrases. We have my favorite one first. Someone broke that. I'm keenly interested in who broke that personally. I don't care about this someone. I want to know who. Something is dirty. Again, I can't clean it until I've been told what's dirty. And then here's a math example. X is an integer. Well, if X is 2.5, it's not. I need more information. I need to know what X is. These sentences have no truth value. That is until we give you more information, until we tell you something about the object. So until the object is defined. You might even say that these statements depend on those objects. Kind of like a function, kind of depends on what you put in to figure out what's going to come out. With that, let's talk about predicate. It's what we've already been talking about. It's a sentence that contains a variable. Basically, you just take a sentence, remove the noun, now you have a predicate. So if we were to use the examples on the last page, we would have X is dirty and X is an integer. And again, these guys have no truth value. So then the question is, so what do we plug in for X? Well, depends on what we're allowed to choose for. So just like functions, predicates have domains. We're going to say that a domain is the collection of things that we can substitute for X so that our predicates become meaningful. For instance, and a domain example for the first one, X is dirty, is we could say every spoon in the world. Now we have things to plug in that would make that meaningful. It doesn't have to be every spoon in the world. Maybe we just mean all the spoons in my house. For X as an integer, we could say that the domain is, we could say spoons. This is nonsense though, don't do that. Okay. But more realistically, maybe you would want to say the real numbers and be like, okay, so pi, no, that's not an integer. But 3, that is an integer. Or we could say maybe just restrict it to all positive numbers, like that. And look at those integers. Lots of choices for domains. Point is, before we start trying to plug things in for our predicate, we first need to know what we're allowed to plug into it. So once we have a predicate which has no true or false value, we really need a domain to be specified. And then once we have those two things, we can use quantifiers to talk about true and false statements for these predicates on particular domains. Two big questions that we can ask about P, and then that'll lead us into quantifiers. First off is P ever true? And is P always true? So asking, is P ever true, is equivalent to saying, can we find an X in our domain such that P of X is a true statement? This is a question of existence. The other question, is P of X always true, is like asking, is P of X going to be true for absolutely every X in our domain? This is what we call a universal statement. I mean, if it's true, it's a universal statement. So that's basically the meat and bread and butter for today. We're going to talk about existence. We're going to talk about universal stuff. That being said, let's apply that to the two examples that we already have. So is P of X ever true when we're talking about the spoons in my house right now? Yes, it is true. I have spoons in my dishwasher. Is P of X always true? So are the spoons that are in my house right now, are they all dirty? No. I have clean ones in the drawer. I promise. Okay. Now, let's do a math example. X is an integer, and our domain is going to be natural numbers, which, if you don't know what a natural number is, we're going to define it to be 1, 2, 3, blah, 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 blah. I'm going to choose to not include 0 because we're going to end up doing some examples where it would be nice to just not have 0 in the naturals. If you don't know, there's some ambiguity about 0 being in or not in the natural numbers. So it's really kind of up to whoever is talking. So next class you hit, be sure to ask, are you going to put 0 into natural numbers so that your professor can also go on this rant? Okay. But is Q of X ever true? Yes. All you have to do is find one example. One is an integer, and it is from our domain of natural numbers. Is Q of X always true? Yes, every natural number is an integer. Okay. So that first question that we're asking about, is P of X ever true? That's a question of existence. That's the existential quantification with the backwards looking E-looking dude. So we write the shorthand of this, and that translates to English. There exists an X in the domain D such that P of X is true. And then if there's exactly one time that it's ever true, we can say that there exists a unique X right there in our domain D such that P of X is true. So let's do an example. We're going to do a different P of X this time. We're going to use X is less than -2. And we're going to look at each of the different domains. So if we've got the domain of the natural numbers, the smallest natural number is 1. -2 is definitely less than 1. And so this guy is going to be false. Never going to happen. But let's expand our horizons a little bit. Let's do all of the integers. So that means we get 0 and all the negatives. And where the negatives is the important part. Does this ever happen? Yes. -3 is an integer and it is less than 2. So now, does there exist X in D such that X is less than -2, which is that statement right there? That is now a true statement. And then this guy is also a yes for the exact same reason. We can just use -3 as our example again. Because if you found something that works and then you just add more things in, Like, it's still gonna work. Still have the same thing that worked before. Which brings us to kind of a useful, or not, it's something that comes up in math. You see existence and maybe it didn't exist. But that doesn't mean you're not interested in it anymore. So mathematicians oftentimes go with like, did this exist? Oh no, that didn't work at all. So let's just make our domain larger and see if we can get it to exist. What's going to happen? For example, we've got, there is a real number such that x squared plus 1 equals 0. False. It only works for x is equal to plus or minus I. Yes, plus or minus I. So if we say, but if our domain were equal to complex numbers, then there exists x in the complex numbers such that x squared plus 1 equals 0 is now true. So that's just, I think, probably the most basic example of, oh man, that didn't work. Well, I would really like it to work. When does it work? Okay. So that's existence. The second question we were asking is P always true? That is the universal quantification with an upside down looking capital A, and we say he stands for all. So if we have the upside down A, sorry. So if we have this upside down A and X is in D, Px, that translates to for all X in the domain D, the statement P of X is true. I don't know why, but some people's brains interpret this better if they substitute the word every instead of all. So it would say for every X in the domain D, the statement P of X is true. Whichever one makes you understand this concept, use it. Universal quantifiers are great because they can help us understand common properties about the domain and derive general conclusions about certain objects. Like if it's always true, I'm like, oh man, these all have something in common. For example, if we look at the natural numbers, oh, that is the wrong kind of n. So natural numbers. If we say for all the natural numbers, x is prime. Like, no. This is false. I mean, all you have to do is start counting. We go 1, 2, 3, 4. 4 doesn't work. 5, 6. 6 doesn't work. Those are natural numbers, and they are not prime. Now we know prime is special. However, if we go, are all the natural numbers integers? Yes, this is a true statement. For all x in the natural numbers, x is an integer. This is, we can conclude, a common trait for our domain. And then just like we did for existence, we played with the domain, we're going to do the same thing with the for all statement. Like imagine that you're looking for somebody to go to lunch with you at a certain restaurant. You're like, I really want to go to, we're going to say True Wine and Deli, because that's my favorite place. If you're trying to find somebody to go with you and you ask absolutely all of your friends, you're much more likely to get an answer. So does there exist somebody that will go to True with you? Probably yes. However, if you're trying to get a group of 10 friends to go to lunch with you, odds are somebody's in there gonna have a different opinion. Be like, no, I want to go to Linda's or something like that. So the smaller your pool is, if you're trying to get everybody to agree on something, the smaller your pool, the better it's going to go. Same principle in mathematics. If we restrict the for all quantifier, if we restrict his domain, it can help us figure out some it helps us decide when a statement becomes true. Just like, okay, so maybe it failed at first, but I'm still interested in all the times that it is true. Let's try and figure out when it's not true and when it is true, and then we'll probably be able to get something really cool out of that. So for instance, let's look at this example. Now we have P of X is positive. We want to determine the validity of, for all X greater than 0, because that's our domain, P of X, rewind. For all X in our domain that we have not specified yet, X is positive, because that's our predicate. And we're going to look at each of the following domains. So at first, if we just do all real numbers, it's very easy, it's very false. -3 is a real number, and -3 is less than 0. Now we restrict the domain a little bit. We're like, well, what about just integers? We're like, okay, still false. Same example, -3, it is an integer, and it is still less than 0. Now if we look at the domain of just natural numbers, this guy is true. All natural numbers are going to be greater than 0 because it goes 1, 2, 3. 1 is the smallest one. Okay. So with that being said, I think we're good on existence and for allness. Remember negation for a minute. Day 1. We said that flips the truth statement or the truth value of a statement. How does that interact with our new quantifiers, existence and universal? There are 2 big rules that link these together. We've got the first one, which is, we'll do for all first. Notice that it flips to an existence. So this is the way I always remembered it. You've got 2 choices. You've got for all and existence. You just flip to the other one. And then, really big notice, the domain stayed the same. I didn't do anything to the domain on this side. So we want to keep the domain, but then we want to negate the statement P. See? There he is. He's being negated. And then the exact same pattern is going to follow for the existence. So if we do existence, we get something involving for all. So we flipped from existence to the for all one. We kept our domain. And then P needs to be negated. I don't know, something about being able to say flip, keep, negate kind of helped me turn the crank on these. Why does this work? Instead of going off on some sort of mathematical tangent, let me appeal to your intuition. Let's go back to our X is dirty example, and we're talking about the spoons in my house. So original statement, if I were to do a for all statement, for all X and D, we get P of X would be the same thing as all spoons in my house are dirty. Let's negate that. So here we go. We've got the negation on the outside. So that would be like if we could just put a not in front of our sentence. That makes grammatical sense. We're okay with that. Not all the spoons in my house are dirty. There you go. That is the same thing as saying you can find a spoon. So not all of them which means you can find one that is the exception to this rule. So there is at least one spoon in my house that is not dirty. Notice how this follows with the pattern that I said before. So we said flip. So this is existence now. So flip. And then the domain stayed the same. We're still talking about spoons in my house. So flip, keep, and then this is the negation of P. So, oops, I should say negate. And then we know what not dirty means in English language. So let's go ahead, take it one more step and say there is at least one spoon in my house that is clean. I promise I do have clean spoons again. Okay. So we did the flip, we did keep, we did negate. It followed that pattern. So negating for all is the same thing as there exists one that doesn't obey this rule. Let's look at there exists. So again, we're going to use the same P and D, dirty spoons in my house. So original statement is there exists D such that PX. There is at least one spoon in my house that is dirty, which is a true statement. But if we were to negate that, you just know from being alive and speaking English, there is not, here we go, there does not exist a spoon in my house that is dirty. We know how to negate that we're just like, okay, if there are no dirty spoons, what does that mean? It means they're all clean. There we go. All the spoons in my house are not dirty, which is all the spoons in my house are clean. So once again, my existence has turned into an all. So we applied flip, and then spoons in my house, my domain did not change, kept my domain, and then I negated P. Okay, and since we know how to apply that like in every day, hopefully that is sufficiently compelling for you that the opposite of for all is there exists. Let's go ahead, let's do an actual math example. We've got one for all. Let's negate the sentence or the statement. So we need to do flip him. We're going to keep our domain. And then we're going to negate this. So this is going to be the same thing as there exists X in the natural numbers such that X is not prime. And then just in case you forgot, that actually has a name. That's composite. So there exists X in the natural numbers such that X is composite. And we're like, just to talk about the validity of these statements, we already talked about all of the natural numbers is not prime, so this was indeed false. So yes, there does exist a not prime number in the naturals, or there does exist a composite number in the natural numbers. So that is a true statement now. Then one last example, we're going to say not exists X greater than 0 such that X is odd. So we're going to flip we are going to keep this, and then we're going to negate this. So that's why, honestly, I've been so persistent about the domain. I'm pretty sure the book did not make a big deal about domain at all. But when you hit analysis, that's going to be really, really important. You're going to have to negate things, and you're going to have this greater than 0 domain, and you need to know that you're not supposed to negate it. We still want to keep the domain. So when we negate this statement, it turns in for all x greater than 0, x is not odd, or you might even say for all x greater than 0, x is even. And I think we can say that. I think 0 counts as an even number. Just in case it doesn't. It's even or 0. Okay. So I think I've made a big enough deal out of the fact that we kept our domain. We still wanted to talk about x's that were greater than 0. So let's really quickly think about the validity of this statement. This first one is true because there are numbers that are bigger than 0 that are odd. In fact, I think all the odd numbers are bigger than 0. And so this one, all the numbers bigger than 0 are even. That is simply not true. All right, so we answered the question, is P of x ever true, and is P of x always true? Big questions for today, and it really depends on the domain that you choose. And I will let you guys play with that some on your own. See you next time.